Okay, so let's continue with our chapter of the electric current. So from the previous video, we actually discussed about the resistivity. So the resistivity is actually defined as the resistance per unit length when its cross-sectional area is 1 meter square. So we did discuss about the resistance of the equation for the resistance. So the equation is actually the rho L over A. So from in this video, we are going to continue with the topics of the resistivity. So we are going to um, move forward with some examples for the questions of the resistivity. So let's move on to the example for the first examples. So for the first examples, so if I have a wire, so my wire is actually the 900 millimeters. So 900 millimeters, we know that is actually times 10 to the power negative 3 meters. Okay, so if my and my cross-sectional area of the wire is actually 1.3 times 10 to the power negative 7 meter square. Okay, so if my R is given, which is 3.4 ohm, so 3.4 ohm, so the question is, what is the resistivity of the wire? Okay, so based on the formula that we discussed from the previous video, which is R is equals to the rho L over A. Okay, so what we need to do is actually substitute all the magnitude, all the information that given. So R is 3.4 and this is rho. Rho is the one that we need to find, and this is 900 times 10 to the power negative 3, and the cross-sectional area of the wire is 1.3 times 10 to the power negative 7. Okay, so what we need to do is actually calculate the value for the resistivity. Okay, so the resistivity, if I calculate it, what I get is actually 4.91 times 10 to the power negative 7 ohm meters. So the resistivity, the SI unit for the resistivity is actually ohm meters. Okay, so to be note that this resistivity is actually a constant, of course. So so each type of wire, different type of wire, has their own different resistivity. Okay, so which say that every different wire has their specific resistivity of the okay, how should I say that? But anyway, they have their own resistivity. Okay, so let's move on to the second examples. Okay, so um, let's move on to the second examples. So for the second examples, so let me just draw for some diagrams as a reference. So this case, the wire is actually not in cylindrical shape anymore. So my conductor is actually in the cubic shape. So let's say this is my I, and okay. So let's say the length of this conductor is actually 6x, and the height for the wire is actually x, and the width, so I should use another color. So the width for this conductor is actually 4x. Okay, so the question is find R in terms of rho and x. Okay, so if I wish to find out the resistance for this cubic conductor, so the formula that we need to apply is actually the same. So this is R is actually equals to the rho L over A. So rho we already have, so we just consider the resistivity for this cubic conductor is actually rho. So rho, okay, so if for the length, so for the length here, if we can see that the direction of the electric current is actually moved from the left to the right. So I can say that the length of the conductor is actually 6x. Okay, so usually if the cylindrical conductor, so the formula for the cross-sectional area is actually pi r square. So in this case, um, the conductor is actually no more cylindrical shape. So insteadly, the conductor is actually in cubic shape. So I can say that the cross-sectional area for the conductor is actually this one, a rectangular shape. So if my cross-sectional area is actually the rectangular shape, so what I can do is actually find out the cross-sectional area of this rectangular shape. So the rectangular shape for this, okay, so the cross-sectional area for this rectangular shape is actually the length times the height. So this is the formula for the area of the rectangle. So if I follow this formula, so what I get is actually the 4x times the x. So since the formula is the length times the height, so what I get is actually the 4x times the x. So this is my formula. Okay, so if I about to simplify it, so this can be cancelled, and 6 over 4 if I simplify it is actually 3 over 2. So this is rho over x. So 3 rho divided by 2x. So this is our resistance. Okay, so this is how we find the resistance in different form of the conductor. Okay, so let's move on to the third examples. Okay. Okay, so actually there's not enough spaces. Okay, so let's move on to the third examples. So for the third examples, so what we have here, so this is the first wire, and this is the second wire, and this is the third wire, and this is the fourth wire. And at the center of this wire we have the small wire. Okay, so this actually present the cross-sectional area of the wire. Cross-sectional area. So this cross-sectional area, okay, so I can see that in this one set of the wire, so this one set of the wire consists of 5 wire which included inside this big set of the wire. So this green wire, I can say that this green wire is actually has the same has the same cross-sectional area. So the cross-sectional area given here is actually okay. So the red one, so the red wire is actually denoted as wire X. So the wire X, the information given is actually the resistivity of rho, so the cross-sectional area of A, and the length of L. So as for the green wire, which is denoted as Y, okay, so Y, what we have here is actually the 3 rho for each wire. So the resistivity is actually the 3 times of the resistivity of wire X. So the cross-sectional area is actually twice the cross-sectional area of X, which is 2A. So the length is actually the same. Okay, so the question is, what is the total resistance that is that possessed by this big set of the wire? Okay, so this is the cross-sectional area. Okay, so let me just think about it. Okay, so if I wish to see the true side of the wire, so what I can see is actually in this form. So this is the first wire, and this is the second wire, and this is the third wire, and this is the fourth wire. So basically the red wire is actually lies in the center of this wire. So this red wire is actually surrounded by this four of the wire. So I can see that from this side, I can see that all of the wire is actually arranged in parallel. So this wire is actually arranged in parallel. So the formula for the parallel wire, so the total resistance is actually equals to the 1 over RT is actually equals to the 1 over R1 plus 1 over R2 plus 1 over R3 and finally plus 1 over R4. And actually there is actually 5 wires, sorry, and finally 1 over R5. Okay, so this will be our total resistance. Alright, so since there's only one wire X and 4 wire Y, so what I can do, what I can write is actually 1 over R1 plus, okay, so since 4 of the green wire is actually the same, so what I can write is actually 1 over R2 times 4, since it has four similar wire. So the final result, what I get is actually 1 over R1 plus 4R2. So this is 1 over RT. Okay, so let me see whether I can drag it down for a bit. Okay, so since R is actually equals to the rho L over A, so from here I can write it as A over rho L plus 4. Okay. Okay, so let me see what is the resistivity. So the resistivity for Y is actually the 3 rho. 3 rho. So this is L, and the cross-sectional area for the wire Y is actually 2A. 2A. So this is 1 over R, of course. Alright, so if I wish to simplify it, so what I get here is actually rho L. So this is 8 over 3 8a over 3 rho L. So if I total it up, 1 plus 8 over 3. So what I get is actually 11 over 3 a over rho L. So this is 1 over RT. So if I wish to find out the total resistance, what I need to do is actually invert it up. So the total resistance is actually 3 over 11 rho L over A. So this is my final answer. Alright, so this is how we calculate the total resistance for this big set of the wire, which consists of 5 wire, which is 4 similar wire and one different I repeat again, sorry. So which consists of 4 similar wire Y and 1 wire X. Okay, so what we need to do is actually observe step by steps. So if we are able to find out what is the arrangement for these wires, so hence we can find out what is the total resistance that possessed in this big set of the wire. So to what we need to be care is what we need to be cautious is the arrangement of these 5 wires. Okay, so I think in this part the most difficult is we need to determine whether the wire is actually arranged in series or parallel. So in this case the wire is actually to be obvious, the wire is actually arranged in parallel. Alright, so we have done for the third examples. So there's actually another examples. So let's move on to the final examples. So for these examples, so consider I have a pipe PVC. So this is my pipe PVC. So this pipe PVC is actually surrounded by the copper wire. So this is the copper wire that surround the pipe PVC. Okay, let me just draw it slowly. Okay, almost done. Okay, so this is the pipe PVC that's surrounded by the copper wire. So this is the copper wire, and as a note here, the copper wire is actually the cross-sectional area for the copper wire is actually the square structure of okay, cross-sectional area. Okay, let me just drag it down. Cross-sectional area. Okay, so this copper wire consists of the square cross-sectional area. Okay, so the information given, the R is actually the R for this, the radius for this PVC is actually 6.0 times 10 to the power negative 2 meter. Okay, so the square cross-section copper wire, square cross-section copper wire. So the square cross-section copper wire, it has the size side of 1.5 times 10 to the power negative 3 meters. Okay, so the number of turns, the number of turns, which is this wire that surround the pipe PVC. So the number of turns is actually 300. Okay, so the question is, find the total resistance of the hollow copper cylinder. So the question is actually asking for the total resistance. Okay, so the total resistance, and to be noted that the resistivity is actually 1.69 times 10 to the power of negative 8. This is ohm meter, sorry. Okay, so the total resistance. Alright, so okay, let me just observe for a while. So the formula that we need to apply is actually the same. R is actually equals to the rho L over A. So the rho here is actually 1.69 times 10 to the power negative 8. So the problem is actually came from this L. Okay, so if we observe from the diagram here, so we can see that the length, the copper wire initially is in the form of straight line. So this straight line is actually allowed to surrounded the pipe PVC. So the surrounded pipe, when the copper wire is surrounding the pipe PVC, so this actually forms the structure of this type of structure. So when surrounding the pipe PVC, so the copper wire is actually become this form of how should I describe this one? Okay, I repeat again. So when the copper wire is surrounding this pipe PVC, so the structure of the copper wire is actually forming a circle. So this is actually the circle here. So I can say that the length of the copper wire for 1 turns. So this actually how should I describe this one? Okay, so this copper wire is actually forming the several of turns. So we consist of 1 turns, and this is the second turns, and this is the third turns, and so on. So for the first turns, for the first number of turns, so my length L, and this for my L is actually the 2 pi r. So my L is actually becoming 2 pi r since the copper wire is actually surrounding the pipe PVC. So my length L has becoming the 2 pi r. So this 2 pi r, if we wish to find out the total resistance, so the 2 pi r should multiply by 300. So this 300 is actually the 300 turns. The 300 turns times the 2 pi r. Okay, so I think I should erase this one first. So I remain this one as rho. Okay, so what will happen for this A? Okay, so if for the A, so the A is actually the square cross section of the copper wire. So since the side is actually the square, so the area for the square is actually multiplication of two sides. So this multiplication of two sides, what we get here for a is actually x squared. Okay, so what we need to do is actually substitute this 1.5 times 10 to the power of negative 3 and bracket square. Okay, so I just write it remain as a, and what we get here is actually 1.69 times 10 to the power negative 8, and this 2 pi r, and this r is actually the radius for the pipe PVC. So the radius for the pipe PVC is actually 6.0 times 10 to the power negative 2, and this is 300. And as I said that, the square of two sides, so this is actually, okay, 1.5 times 10 to the power negative 3, and this is square. Okay, so what we get here is actually 0.849 ohm. This is my final answer. Okay, so this is how we calculate for the total resistance which possessed by the hollow cylindrical tube. Okay, so hollow copper cylinder, sorry. Okay, so we have done for the resistivity. So let's move on to another subtopics. Okay, let me just zoom it in. So we came across the new subtopics. So the new subtopic is actually talk about the conductivity. Conductivity. So just now we talked about the resistivity, and now we're going to talk about the conductivity. So the conductivity is actually the reciprocal to the resistivity. Reciprocal to the resistivity. So since it is reciprocal to the resistivity, so the formula is actually which is the resistivity is equals to the 1 over conductivity, which is sigma. So rho is actually equals to 1 over sigma, and this is the formula. Okay, so if I have my formula, which is resistance equals to the rho L over A, so what I can do is actually convert it into the sigma, which is L over sigma A. And this is another form of the resistance. Okay, so this is the briefly introduction for the conductivity. Alright, so this is the basic introduction for the conductivity. So we're going to talk about the relation between the current density and the conductivity and the electric field. So we're going to look about the derivation of J is actually equals to sigma E, and J is the current density, and this one is the conductivity, and this one finally is the electric field. Alright, so where should I start? Okay, so for the basic formula, which is J is actually equals to I over A. So J is actually equals to I over A. So this I convert it into V over R, 1 over A. So since the Ohm's law tells us that V is directly proportional to I, and V is actually equals to IR, and I is actually equals to V over R, so I substitute this one into here. Okay, so I know that the R is actually equals to the A over rho L. 1 over r is actually equals to a over rho l, and this is a, and this one can be cancelled, and this one remain as j, of course. Alright, so what I get here is actually 1 over rho. The remaining variables is actually 1 over rho, and this one is actually v over l. So we know that v over l is actually the electric field. Okay, so this is E, and this is 1 over rho. And as we discussed from the introduction of the conductivity, which is the conductivity is actually reciprocal to the resistivity. So what I get here is actually the sigma E. So this is the relation between these three variables, which is current density and the conductivity, and finally the electric field. Alright, so this formula that we derive from the basic formula of the current density. Okay, so this formula is actually equivalent. Okay, let me use another color. So this formula is actually equivalent to the Ohm's law. So it means that if we use the equation of the Ohm's law, we actually are able to derive from the Ohm's law into this formula. So what we need, let me show you that. So from the basic formula of the Ohm's law, which is V is actually equals to IR. So if I wish to find out this formula, so what we need to do is actually divide the both sides by L. So this is L and this is L. Okay, so this V over L basically is E, and this remain as IR over L. Okay, so I just write this side. Okay, so E, and since R is actually equals to the rho L over A, so this is I over L, and this is the rho L over A. And this one can be cancelled, of course. And I can say that I over A is actually the current density. So I over A basically is equal to J. So this is J rho. So as we learned from the previous parts, so the resistivity is actually the reciprocal for the conductivity, which is 1 over sigma. So finally what I can do is actually move this sigma to the other side. So finally J, which is the current density, is actually equals to the sigma E. And this is the derivation, which is equivalent for the Ohm's law to the Ohm's law. Okay, so I have proved that the formula J is equal to the sigma E is actually equivalent for to the Ohm's law. Alright, so I think we are done for this subtopics. There's actually remaining one more subtopic, and we shall discuss in the next video. So I think we stop here now. If there's any question need to be asked, please comment below this video, and I'll see you next time. Thank you. Bye.